Hi, welcome back to our machine learning course. This is the last video in our lecture on neural networks. So previously we've seen how neural networks work and how to implement them in practice. Now we'll see how to use them in practice and how to do model selection to get the best models. Now we've seen model selection extensively, and so we've seen that in many cases we have algorithms which have a lot of hyperparameters and need to be tuned. And we can typically do that with something like cross-validation. The problem with neural nets is that just one training run is so expensive that we typically don't want to wait for an entire cross-validation to finish. And we typically want to look while the model is training to see if it's going anywhere or not. Right? So compared to the more robust algorithms that we've seen before, such as support vector machines or random forest and so on, or boosting, these are pretty much sure to converge. Not always, but they're pretty robust, right? We can assume that they converge. With neural nets, this is not so clear. So yeah, we want to actually look at the learning curve to see whether our model is actually going anywhere or whether we need to completely change it. Neural networks are also very easy to overfit, and there's a range of regularization techniques we can use to reduce overfitting. Some of them we've already seen, and some of them are very specific to neural nets. And that's what we'll discover in this course. So there's many questions you want to answer. First of all, how many epochs do you want for training? So you can do that by training a neural net and then tracking the loss after every iteration, so after every epoch or after every batch update. In this case, we plotted the epochs here. This is actually plotting this is quite easy because most algorithms have a callback function. It looks a bit like this. So when you do fit, you can add a callback. And in this case, you can also add a callback which plots these graphs, which is what I do here. Right, so every time an epoch finishes, it sends an update to my plotting function, and then this gets plotted in real time. Yeah, so if we observe this, we get the learning curve, right? So first of all, we have the training loss. So this is the loss function. This goes down, and we can see it keeps going down. This is expected. This is exactly what backpropagation does, right? It updates the weights so as to minimize the loss. The loss on the validation set does not go down so much. So in the beginning, it goes down a little bit, then optimizes here around 0.4-ish, and then goes up again. Right. This is very typical. In this case, you could loosely translate this as underfitting in this region. Then here it's more or less, yeah, it's already overfitting a bit, of course. This is the optimal region, and here it's definitely overfitting. And you can also see it here. So here we have the training accuracy, and here we have the validation accuracy, and you can see these gaps get bigger and bigger. So it's definitely overfitting here. Right? We don't want any gap between the two. So let's see how we can fix that. First of all, we talked about early stopping before, right? So a cheap way to avoid overfitting is to just stop training. We can just decide at some point, okay, stop here, don't train anymore, because if you keep training, you will start overfitting too much. So that's definitely something that's often done. It's called early stopping. And the idea is typically you observe the curves, and especially the validation curve here, the dotted blue line. And if this no longer improves or goes up, then you just stop the training. There's different ways of doing that. Ideally, you use some kind of moving average over it, but you can also just use a number of steps without improvement. This is this patient parameter here, 3. This means that if there is no improvement in the last 3 iterations, you just stop training. Yeah, and you can add those early stopping functions to a callback. You just add this to your fit function, and this will, every time an epoch finishes, it will call this function, and this can then send a signal back that it should stop training. Another thing you want to tune, so likely we are overfitting here because we just have too many nodes in the network. Right? We had 2 layers of 512 nodes, which is a lot. So maybe you want to reduce that. So the number of learnable parameters is also called the model capacity. And we say that a model with a lot of parameters has a high memorization capacity, which means that if you have a network with a large number of parameters, it can start overfitting rapidly, and it can start basically memorizing the training data. Right? The training data is stored exactly in the weights. And sometimes you can even demonstrate that by activating some of the layers and looking at the activations, and the activations like show you individual images in the training, for instance. This is an extreme case. You want to avoid that at all times. Right? You don't want to have your network memorize the entire training set. That's not good. It means you're overfitting, and your network will not work well in practice. It will not generalize very well. Right? So you typically want a smaller model, so you force it to learn a compressed presentation which generalizes better. And there's different ways to do that. So you can either start with a few layers and a few nodes, and then gradually increase until well, the returns diminish and you don't get any improvement from adding more nodes. Or sometimes you can go the other way around. You just add a large network and you remove layers or you remove nodes until, well, the overfitting doesn't improve anymore. So in this example, I reduced my network to 256 nodes in the first layer and only 32 in the second layer. I get a very similar performance, and I get slightly less overfitting. So here it was stuck at around 4, and here it goes, well, around 3-ish. So it's slightly better, at least, if you look at this here. Interestingly, the difference with the accuracy is not that big. It's only like 0.5%. So yeah, but at least in terms of the validation loss, there's an improvement here. The opposite of capacity is bottleneck. So that's when you have a network with too few nodes, right? So imagine you have a very large input layer, and then you have like just 2 or 3 nodes here, and then again a large output layer, right? This means that all the information that's in your dataset has to be encoded in these 3 nodes. And actually, this is something that is actually useful. This is called autoencoders. So here you want to represent your data set in as few parameters as possible. There's many useful applications. When it comes down to training networks, having a layer that's too small will probably cause you to lose information. So you don't want that. So all the information has to go to this bottleneck, and this can reduce performance. So yeah, in this case, I went a little bit extreme, so I have only a bottleneck of 2 nodes, and we see, well, overfitting is gone. So the difference between the validation loss and the training loss is almost 0, except at the end a little bit here. Before accuracy is almost nothing. But we do see that our best training loss is now somewhere here around 0.7, while previously this went down to 0.2, right? So the bottleneck that we introduced here definitely makes it impossible for the model to learn a good model, right? We're definitely underfitting in this case. All right, so another better way of reducing the complexity of the model is to add regularization. And in all the classical machine learning algorithms we've seen, we've always been able to do something like L1 or L2 regularization, and we can do the same here. So the principle behind L1 and L2 regularization is just to force the weights to be small, right? And this is exactly what we do here as well. So we can add to the layers what's called a kernel regularizer, and we can again choose between L1, L2. We can also have both. There's a regularizer which is L1 plus L2, and we can set our alpha parameter. This is the amount of regularization, and this is basically an extra dampening on the weights. So we kind of force the weights to be small, in addition to any changing they do in terms of the gradient updates. So yeah, this kind of forces our weights to be smaller than otherwise. So yeah, it's a type of regularization. And again, we can choose between L1 and L2. L1 will cause many of these weights to be exactly zero, and this will cause a sparse network. So imagine that you have two layers and they're fully connected. Then with normal L2, you would just reduce some of these weights to small values like 0.001. While in L1, it may set this to 0. And setting a weight to 0 means that this weight is simply gone, right? So if you plot that differently, it means that only a few connections remain and all the other ones are set to 0. It's a sparse network. While a regularization will keep a dense network with many, many small weights. In our data set here, definitely overfitting has been reduced. So we had this pretty sizable gap here, right? If I just add with regularization, I have here a network which is 265 by 128, okay? Somewhere in the middle of what we had before. And we add the regularization, and we see that the gap between validation loss and training loss is smaller, so it's definitely overfitting less, but it's actually underfitting a bit. Performance here is a bit lower than we had before. The loss gets stuck here at 0.4, so this is probably underfitting a bit, right? So you can choose to either reduce this alpha parameter more, like 0.0001. Typically, there has to be smaller for neural nets, and see if that works better. Right? This is definitely something you can try. Right? So whenever you see that your model is overfitting, it makes sense to try adding L1, L2 regularization and see if it improves things. There's, however, another way which is simpler and typically works better, and that's called dropout. So the idea behind dropout is to set some of the activations for every layer at 0. Right? So it means that if we have this simple network with these 3 hidden nodes, and we would have a dropout rate of 0.3, it means that any iteration, you would randomly set one of these activations to 0. Basically, temporarily disable this node entirely. And in the next iteration, we set another one to 0, and the next iteration, we set another one to 0. But overall, on average, we hope that each of them will be set to 0 on average. Yeah, and the reason why this helps is that it avoids that some of the neurons will encode some of the data, will learn patterns, will overfit. So some of these nodes can learn patterns which happen to be in your training set, but which are basically noise or not very interesting for to make predictions from. And by setting some of these outputs to 0, you break this effect. Right? So say that this node here learns, say that the input is a number here, and this neuron learns some kind of, I don't know, weird shape. It should be deeper than that, by the way. It learns some pattern in the data, which is purely noisy, right? It could be that later neurons in the network then start using this pattern to learn abstractions from, right? And if this is a noisy pattern, then you don't want that. And so by setting these outputs to 0 once in a while, it allows other neurons down the line to forget about this pattern and learn from other patterns that are hopefully overall more truthfully than the ones that we disabled here. Right? And so by randomly shutting off some of these nodes, we have a penalty, of course, right? We lose some activations. It may slow down learning a bit, but we're less likely to overfit on specific patterns that we find in our data set. And that's the whole idea here. Right? So you break up any accidental non-significant learned patterns in the data. Now, you can only, of course, do this at train time. At test time, you have to now make a correction because this node here expects a certain amount of activation, and say that you have a dropout rate of 0.3. That means it only gets 0.3% less. It gets 30% less activation from these nodes, right? And so at test time, we solve that by basically reducing all the outputs by that amount. So to just simulate the same effect that we saw during training. Okay. Right. That's dropout. Now dropout, well, in principle, this is something that is done inside a node. This is often implemented as a layer. This is probably a bit counterintuitive, but say that you have a layer like this, you can add a dropout layer, and this dropout layer is special because it has the same number of nodes and they're connected one-to-one. And basically what this does, this internally will make sure that some of these are shut off at some points randomly. Right? This is what the dropout layer does. So if you want to add dropout, you add it as an extra layer and you have to set the dropout rate. 0.5 is pretty large. You shouldn't go much larger than that. Typically it's between like 0.1 and 0.5. Now if we do it in our data set, we can see that, well, validation loss goes down. So it's definitely overfitting less. And yeah, we get about maybe slightly better, but the difference is not so bad, not so large here either. Right? So there's definitely a regularization effect. Whether dropout is better than the other types of regularization that we've seen before, that's debatable. But overall, it's a pretty solid technique that you should definitely try. So whenever you see that your network is overfitting, try to add at least a bit of dropout and see that it improves results. A final technique, this is not actually a regularization technique, but it definitely helps against overfitting in some way, and that's batch normalization. So we've seen before that if you have a neural network, we definitely want to normalize the data that we give to our input layer, right? Because we want this to be, well, the mean of this should be close to 0 because it makes conversions easier, it makes training easier. Now, it's of course possible that as data gets through these layers, at some point the data that we pass or that is produced by a layer is no longer normalized. And then you will get the same problems. You will get the vanishing gradients and you will get exploding gradients. And you don't want that. So the idea to solve this is to normalize the data in the middle of the network. Right? So we have a normal network, and in the middle we add layers which normalize the data. Now, because data goes to the networks one batch at a time, we can only normalize over that batch, right? And that's why we call it batch normalization. Right? So the whole idea is that we have a batch of data, it goes through the network, and at some point we take that data, we normalize it, and then we give it back to the next layer. And we can do this multiple times to the network. So this is a very effective method against, for instance, vanishing gradients. And this effectively allows us to build much deeper networks than otherwise possible. So whenever you see that your model is not learning, it may be because of this vanishing gradient problem, and batch normalization may actually help you to train your network. So the way it works, so within a batch, we normalize data, so we set the mean deviation close to 0, deviation close to 1, so this is standardization. And also across batches, so if you have a new batch coming in later, we remember the average, the mean that we had. So we keep a memory of all the previous means that we observed throughout the batches. And we use an exponential moving average over the batch size, mean, and variance to have some memory of what the data looked like in the previous batch. Right? If you would not do that, then the normalization may differ a lot between batches, and you don't want that. So by keeping this moving average, you do keep some information from previous batches, and you have a much smoother normalization. Right? Yeah, and the goal is to have deeper networks which are less prone to vanishing and exploding gradients. You do this by adding again a new kind of layer, which is a batch normalization layer. So you can, well, it's probably not necessary after the first layer, but you can definitely do it if you want to. So we add normalization, and we do dropout, and then we have a new dense layer. After the dense layer, we again do normalization, again dropout, new dense layer again. So you can keep stacking those 3 layers together. You don't have to all the time. You can skip a few, of course. It really depends. You can play around with different, but this is a pretty standard way of doing things. So first of all, what we see here is that we start with a large initial layer. We add normalization and dropout for regularization to make sure that the gradients don't get lost. Then we have a smaller dense layer with even smaller ones and a smaller one. This has kind of also known as a pyramid shape. So the first layers are larger, and the next layers are increasingly smaller. And if we see what that does to a model, we see that, well, there's definitely less overfitting or validation loss. Well, it's actually lower than the training loss. And in the end, it's very close. There's almost no overfitting happening whatsoever anymore. Also in the training accuracy, there's no overfitting happening anymore here. It may still be underfitting a little bit, so you may go back and try to reduce the dropout here. So yeah, you can play around with these values and see if you can get better performance out of this model. Okay, so typically you have to tune many hyperparameters, and you can do this manually, and many people do. Right? Over time you get experience. You know what's important to tune, and many people tune their neural networks manually. In some cases, you can use stuff like random tuning, random sampling, and grid search, random search, and so on, to see if you can find better learning rates, better batch sizes, and so on. So you can definitely tune a lot of hyperparameters in these neural nets and see if you can get a slightly better performance out of it. Keras has a built-in random search. It looks like this. So Keras tuner has random search, and you can do random search over a function model. And this model has this interface. So it has a dense layer where the unit is sampled from this distribution, right? So it's an int with between 32 and 500 and step size 32. If you want to try different learning rates, you can do that as well. You can add a hyperparameter choice, and learning rate is one of these guys. And you can then give this to the Keras tuner and then let it tune your hyperparameters. You can also wrap this in scikit-learn. So there's a scikit-learn wrapper for TensorFlow. This will basically wrap a Keras model so you can interface with scikit-learn. So if you want to do grid search or random search, you can do it as well with scikit-learn. There are a lot of other techniques. There's a large field of research called automated machine learning, which tries to be more clever about this. And there's techniques such as hyperband, which typically work a bit better than random search to tune these parameters. And there are also other techniques that not only tune your hyperparameters, but even search the space of all possible networks to find the best one. It's a big field of research. I will come back to that in a later lecture. Right, so that's all. So we've covered quite a bit of ground. We've seen how to construct neural networks. We've seen how to train them, how backpropagation works. We've seen how to choose activation functions, how to initialize all weights, how to choose the optimizers. We've learned how to implement neural networks in practice. And we've seen several techniques that you can use to do model selection, such as early stopping, defining the optimal number of nodes and layers, L1, L2 regularization, dropout, and batch normalization. So I hope this was useful. If you have any questions, of course, as usual, you can post them in the comments, and I hope to see you in the next video.